Okay, so we're going to continue our discussion about waves, and specifically we're going to talk about light waves and a subunit that we call optics. And optics deals with the behavior of light waves, especially when they pass either through a lens or bounce off of a mirror. So we're going to start with the simplest case today, and that is talking about what we call a plane mirror. And a plane mirror is just that. Plane literally means flat or a smooth surface. That's where Plano got its name. And so this mirror it's flat. It's a flat surface. And so I imagine having these 5 students. I've just named them A, B, C, D, and E. And this is a top view of them sitting in a row in a class. And then there's this mirror at the front of the room. And as I mentioned, it's a plane mirror. It's a flat mirror. It's not curved or a funhouse mirror of any kind. And so what happens with this mirror, and why do certain students see other students, and where do they appear to be? Well, first of all, let's talk about why you can see student E at all to begin with. If you're anywhere in the room, you are able to see student E because light from either the sun outside or the light fixtures in the room bounce off of E, and those light rays reflect and radiate off in all different directions. And if any of those light rays reflect off of E and hit you in the eye, then you can see E. You perceive E where they are, and that's because those light rays bounced off of E and arrived at your eye. And so I want to look specifically at one particular ray. Oh, sorry, just kidding. First, let's talk about what you were reminded of in the video from Bozeman Science, and that is that when a wave reflects off of a surface, then the law of reflection states that the incident angle will be equal to the reflected angle. So these 3 rays here, I've shown how they're going to bounce off at the same angle as they came in. And you see that, with bouncing a ball on the ground, right? If you make it hit the ground at a steep angle, it's going to bounce back up at a steep angle. If you make it bounce at a shallow angle, it'll bounce off at a shallow angle. So now I want to turn my attention to one specific ray, and that's this ray. This green ray is I'm just highlighting one particular ray that leaves student E. As it travels in a straight path, it hits the mirror, and it's going to reflect. Again, angle of incidence is going to equal the angle of reflection, and so that ray is going to hit student A in the eye. And so student A will see student E. And then because our brains are busy trying to do things, they're trying to keep our heart pumping, and then think about what we're going to wear tomorrow and those kinds of things, our brain takes shortcuts to make things more efficient. And so one of the shortcuts that our brains take is it assumes that every ray that hits it, every light ray that hits it, did so by traveling in a straight path. And so we trace back where that light ray looked like it came from, and that light ray looks like it came from this position over here on the right. And so according to E appears to be at that location on the other side of the mirror. We can do the same thing with this particular light ray. Again, I'm just highlighting a light ray that's bouncing off of E. This particular one, when it hits the flat surface of the mirror at the bottom, because the law of reflection will bounce up at this angle, and that one hits student B in the eye. And as a result, student B also sees student E, and because student B's brain is taking shortcuts and assuming that light ray that's hitting in the eye followed a straight path, we can trace it back. And so E appears to be at that location for student B. And notice they're the same. But now look at this. What about student C? Is there a light ray that can bounce off of student E, hit the mirror, and then, following the law of reflection, hit student C in the eye? And the answer is no. There's not a ray that can both bounce off the mirror and go from student E to student C, and therefore student C cannot see student E in the mirror. And so let's kind of do a quick evaluation of this. Let's look at the 5 students again, and I'll ask you a question. I say, can student C see student A? And so to answer that question, you ask, okay, is there a ray that can start on student A, bounce off of the mirror following the law of reflection, and hit student C in the eye? And the answer is yes, it's that ray. And so yes, student C can see student A. So then I ask, well, can C see B? And you say, well, there's that light ray. And so yes, student C can see B because that light ray leaves B, hits the mirror, bounces off, and hits student C in the eye. And then, of course, the question that just begs to be asked is, can C see C? C. Yeah, of course, the student C can see themselves in the mirror because the mirror is perpendicular to them, right? And so any light rays that leave them, that hit the mirror, will bounce straight back to them. Now, if you went and tilted the mirror, would there be any light rays that could then bounce back to where C was? The answer is no, and that's why whenever you're trying to line up a mirror for somebody else from a far distance away, little tiny changes cause them not to be able to see themselves anymore. All right, so then speaking of seeing themselves, let's look at how you look at a normal plane mirror in the house. Well, the reason you can see yourself is because light rays leaving your feet, for example, hit the mirror and then bounce off, obeying the law of reflection, and hit yourself in the eye there. And then, of course, your brain takes a shortcut and says, oh, that light ray must have originated over there. And by the way, forgive me for not making that straight. I didn't have a ruler at home. And then there's another light ray that leaves maybe your midsection, your arms. It hits the mirror at a higher point, right, and reflects, obeying the law of reflection, hits you in the eye. And so your brain traces that back and says, okay, that came from there. And then finally, let's pick just one more ray, maybe one that comes from the top of your head, bounces off the mirror and hits you in the eye, and your brain traces that back from where it appears to come from, and it seems to come there. Well, as a result, your brain puts all those light rays that are originating and hitting you in the eye, and it re-puts them together, assembles them, and you see what we call an image. And the image, you'll notice, is on the other side of the mirror. And then we have these distances. We label them object distance and image distance, or D sub O for the object and D sub I for the image. And again, if I'd drawn this to scale, if I'd been a little more careful, you would notice that for a plane mirror, right, when you see yourself on the other side of the mirror, what do you know about the object distance and the image distance? Well, they're the same, right? If you move closer to the mirror, what does your image on the other side seem to do? It seems to get closer to the mirror as well. And if you move farther away, the image distance seems to get farther away. And so this is how you see things in mirrors. It's a combination of the light originating or reflecting off of a surface and then bouncing off of the mirror. And then when your eye perceives it, it traces it back to where it looks like it came from and assembles it in the form of an image. And then you see that image on the other side of the mirror, or you appear to see something on the other side of the mirror. Now, obviously, there's not anything on the other side of that mirror. If you've been in a restaurant that has a wall of mirrors, that's because it gives the effect of there being an equal sized room on the opposite side of the mirror, and so a restaurant appears larger, when in reality, there's nothing on the other side of that wall except for, that other shop or whatever. And so that's why mirrors are often used in optical illusions like that one. That's where the phrase smoke and mirrors comes from, right? If you're trying to deceive somebody. Anyways, so this is just a quick primer on plane mirrors, and you're going to use this information now to answer the question of how long or how tall does a full-length mirror have to be.